right, and welcome back. We're finally finishing up our last step of our titration curve, and we'll move into buffers. Now, at this point, we're at 30 mLs. We are past the equivalence point. If we did our voom, we would find, remember you have to do your dilution. We add volume to volume. I'm not going to do that calculation because you should know how by now, but I will put down the results. Our hydroxide after dilution, after our voom, is 0.0857. And our acid was 0.0571. So we did our dilution. This is our stoichiometry. So that's our start. This is our limiting. A stoichiometry goes until the limiting runs out. So we're going to lose 0.0571 minus 0.0571 and plus. And there's our water. All right. Now that goes to 0. That's 0.0571. Now this is pure hydroxide. It's like adding, that's just excess strong base. Now when you have an excess, we want to always evaluate, we have an excess strong base here, and we have a weak base. Now that weak base is going to react with water, and it is going to contribute some hydroxide, but it's going to be very small. In fact, when I calculated it, if that's all that was present was just this weak base, it would contribute a hydroxide of 6.63 times 10 to the minus 6. When we compare it to this, even if we added it straight, it's not quite as simplistic as that, but if we added that straight, this is negligible. So any contribution from our weak base is very small compared to this excess strong base. And so we're just going to get our pOH from that. So our pOH then would be minus the log of 0.0286. And that's 1.544. So my pH, let me put it up here because I'm not sure how much the video is going to cover there, the screen. It's 12.457. Now that's why when you saw that series of titration curves in the inquiry, if you notice, remember they all had different starting amounts? They'd all start at different places, but they all ended at the same place. And they all ended at the same place because that's leftover excess strong base. And so they're ending at the pH defined by the excess strong base, not defined by how weak the acid was. Okay, so that's it. You've done a titration problem. You're not going to have to do too many of those on a test. They do take a long time, but they also really demonstrate every kind of problem we're going to come across. They demonstrate a weak acid problem, they demonstrate a buffer or common ion question, demonstrate a weak base problem, and they demonstrate a pure stoichiometry problem. Now, I want to show you the alternative to having to do a full rice. Some people don't teach it. I really like it. I'm not going to derive it, but if we took minus the log of both sides of a Ka or Kb expression, we would end up with what is called the Henderson-Hasselbach equation. No, not the David Hasselhoff equation, the Henderson-Hasselbach equation. And this can be used with only a couple of situations. For one, you have to have a weak and its conjugate present. In other words, we need to be in the buffer zone. Okay, the buffer zone has a weak and its conjugate present. Now, there's a form for a weak base and there's a form for a weak acid. Now, if we took minus the log of both sides, we would end up with the acid form of this. Okay, and it gives us a shortcut. So if we're starting here and we need to end way over here, instead of having to follow the maze through DSE and all of that, we get a shortcut at least on the equilibrium. Okay, you still have to do the doc saves, but you can do doc saves Henderson-Hasselbach. Okay, we're really stretching these acronyms here, okay? It's a shortcut through the maze, and you are allowed to do it only under a few conditions. One, you identify that you have an acid in its conjugate base. This can be the buffer zone of a titration, or you could have a weak acid plus a salt of the conjugate base. That's why it was so important. That's why I wanted you to recognize what a salt of the conjugate base looked like. Okay. Now, you also have to have a situation in which your initial concentrations are greater than 100 times Ka. In other words, ones in which we can neglect that plus and minus A or plus and minus B. So if those are both true, you can skip rice and use this Henderson-Hasselbach equation, which is really just your Ka rearranged. If you take minus the log of both sides and do a little rearrangement, you get this equation. pH is equal to pKa. That little p just says take minus the log of, so that's minus the log of your Ka. And that's important to know because some tables report pKa values instead of Ka values, plus the log of your conjugate base over your original acid. Now, the base version of that is POH is equal to pKb plus the log of your molarity of your conjugate acid over your molarity of your original base. So that would be the base form of that. And I personally like this equation. I think it's really helpful. And we will move into those calculations when we get to our next series of slides, because I just realized I'm out of slides on this. So, short little video to finish up some final details. Let me do the one thing though, since we have just a second on this video. If you take a look at this, if you are at the equivalence point, by definition, if you are at the equivalence point, those are the same. So what you would have is plus the log of 1. So the log of 1, hopefully you know that, is 0. So that's another way of proving that your pH is equal to your pKa at the equivalence point, right? Because whatever this is, let's just say it's 0.5 over 0.5. That's 1. The log of 1 is 0. That goes away at halfway at the volume of your equivalence point. I might have misspoken and said at the equivalence point, but that was wrong. Halfway to the equivalence point, these two are equal, and pH is equal to pKa. All right, that's it. We'll start talking about buffers next. Until then, this is signing off.